So this video talks about the basics of Newton's law of cooling. So Newton's law of cooling is an application of first order differential equations. A specific question you get on Newton's law of cooling does depend on, well, the physical situation you have. So here's what's going on. Newton's law of cooling looks at when you have an object and we measure the temperature of that object at a certain time. So capital T represents temperature, lowercase t represents time, and this object is immersed in some medium that has a constant temperature of m. And the thing with Newton's law, it says that the rate of change of the temperature of your object is proportional to the difference of the object's temperature versus the medium it's in. Now, when we say medium, there's a lot of different things that you could do, but one of the sort of classic things that people talk about when you first start looking at Newton's law is things like, what's a classic one? Cooking something in an oven or in a microwave. Okay, the classic question I'm thinking of right now is something like you cooked a turkey in an oven. You put the turkey in the oven. The oven was set at a certain temperature, so you know that the turkey got up to that temperature. You took the turkey out of the oven, so it had a set temperature for whatever the oven was set at. You put it on the counter. Now it's in room temperature air. How long is it going to take for that turkey to cool down to a non-burning your mouth temperature? Okay, that would be a Newton's law, or not Newton's law of cooling situation. Now, let's look to see what this would look like in terms of symbols. In terms of symbols, this rate of change talks about your derivative. So this is the derivative of the temperature function as relates to time. And that's equal to the proportional here means there's some constant. That constant is specifically dependent on your situation. So that's going to be dependent on whether you're talking about a turkey or whether you're talking about a cup of coffee, whether you're talking about whatever it is you're talking about. Okay? M here is the actual temperature of the stuff you're in, like air if you're in a room. If you're sitting actually inside of some other liquid, it would be the temperature of that other liquid, etc. Minus the actual temperature of your object. This T here, remember, is your function, your dependent variable in this situation. So let us look at an example. And in this particular case right now, the example is just the formulas. What would you do if you were given one of these questions and you wanted to solve it? Okay. So, if you wanted to solve for temperature, T, your dependent variable. Notice this guy, K, is always going to be a constant. M is typically a constant. There are some adjustments to this where M doesn't have to be a constant. But in this case, we're going to be looking at straightforward Newton's law of cooling. Both K and M are constants, which means the only variable in play here is your dependent variable. Notice what that means. That means right now we're in the format of a separable equation. Okay? So what can we do? We could always pull this part here that has the T and the M over to the other side, and then multiply both sides by dt, where that's the differential with respect to time here. At this point, we're separated all of our dependent variables on the left-hand side, all the independent variables on the right-hand side. Remember, K is just a constant. Now, you might have noticed I was also a little bit sneaky here. I actually factored out a negative symbol. And I only did that to make the integral easier to calculate in the future. It's not something that's necessary in any way, shape, or form. Okay. So then we integrate, so we take the integral of both sides. And when we integrate on the side with a little t, well, notice it's just a constant, so that antiderivative is going to be k, whatever the constant is, times little t. But over here, this guy is actually going to turn into a natural log. Remember, shortcut for natural log is if you can take the derivative of the bottom and find it up top, that means you are a natural log of whoever's on the bottom. Notice here the derivative of t minus m is 1, so this side is going to be natural log of t minus m. Oops. Now at this stage we want to go ahead and solve for capital T, because typically we then want to do something with that function. Technically speaking, we do have the implicit solution right here, which is perfectly fine. Okay? It all depends on whether you need to do something with your temperature function. So to solve for t, you raise both sides up to the exponent of e, One side cancels, so we'll just get a t minus m on the one side. And over here, you're going to have t raised to the negative kt plus c. And remember, we did this trick before. This plus c is actually what? E raised to the negative kt times e raised to the c. So that bit is just a constant. We're going to go ahead and rewrite that part that was the constant as an a out front. This a is the same thing as our e raised to the capital C. Lastly, or last thing that we do, go ahead and add that capital M to both sides. And notice this now gives you the general format of what the temperature function from a Newton's law of cooling problem is going to look like. It's going to be whatever the room temperature is, or whatever the temperature of the surrounding medium is, plus some constant times e raised to the negative kt, where little t there is time, and the k is some constant that you'd have to find depending upon whatever object is warming up or cooling down. So let's look at an actual example now. And so a side comment, if you'd solve this differently, where you didn't factor out the negative like what we did, that can cause your answer to change just a little bit. And it's just the format here of whether you'll have a plus or a negative in front of the capital A. Notice that the capital A is just some constant you'd have to solve for anyway. So whether you have in symbol form plus capital A or minus capital A, it's not going to matter, because once you go ahead and plug in any of your data points, your initial conditions, you'll get to the same answer at the end. All right, so let us look at an example. And I've actually got two examples that I tend to do in this section, which one of them starts off, which we've got right here, which deals with blood plasma. So this says that, hey, you've got blood plasma and it's stored at 40 degrees Fahrenheit, but that's too cold to use. So before the plasma can be used, it has to be at 90 degrees Fahrenheit. So the place that we're looking at apparently has some oven, I'm assuming a microwave, that warms this up, hopefully a medical grade microwave. And so the plasma is going to be placed inside of this oven. The oven's set to 140 degrees Fahrenheit, and it takes it 45 minutes to warm up if you have those situations. So what we want to know is what happens if somebody raises the temperature on this oven. I'm hopefully thinking a microwave here of some sort. What if they raise the temperature of this oven up to 140 degrees Fahrenheit? In other words, how long would it then take to warm up the blood plasma? And hopefully, intellectually, you're thinking of this logically, and you're thinking to yourself, shorter than 45 minutes. Okay? The question, of course, is how much shorter? So a couple of things that are key here, and the key things are, of course, in a story problem, your key numbers. If you haven't used all of your numbers, sometimes you have extra information, but especially at a level of class that we are, you're typically going to use all of your numbers involved. So key numbers here, 40 degrees Fahrenheit, which is the initial temperature of your blood plasma, 90 degrees Fahrenheit, which is what we want the end temperature of our blood plasma to be. The surrounding temperature for the oven is at 120 degrees Fahrenheit or 140 degrees Fahrenheit, and the time it takes for your blood plasma to warm up. So let us put this in. So we're going to go ahead and I'm going to tag this as the first oven and the second oven because we've got these two different temperatures. That's just for convenience sake. Okay. So when we're using this first oven, the 40 degrees Fahrenheit is your initial temperature. 45 minutes later, your blood plasma is supposed to be at 90 degrees Fahrenheit, and we know our surrounding temperature here is at 120 degrees Fahrenheit. And I just dropped all the units off here because everything's already consistent in our units. Now, literally just our slide before, we had determined the format for the formula for the solution of a Newton's law of cooling problem. So because we just did those calculations, I'm going to go ahead and jump and plug things in. Okay? So in the formula that we found before, we said it was m minus or plus a times e raised to the kt. M here, the surrounding temperature. We'll go ahead and plug in right there, and now we just have to solve for a and k. Please note we have two pieces of information here. We have two unknowns. We'll totally be able to solve for both a and k. Okay. So when we solve for a and k, I'm going to go ahead and assume that you guys can do that. I'll to the side show the setup. So in terms of the setup, t equals 0. We would have 40 equals 120 minus a e to the 0. So this means when you rearrange, we would have what? Negative 80 equals negative a. So a would equal 80. Okay? Now, that takes care of the first initial condition. The second piece of information we have is the ending temperature. So there we would have 90 degrees equals 120 minus a e to the negative k times 45. And if you want to change these units on time from minutes to either seconds or hours, which are seconds are really common, but again, sometimes it's years, sometimes it's hours, sometimes it's minutes. In this case, there's no real reason to change these units from minutes, so I went ahead and just put 45 up there in the exponent. Notice we already know what A is, so I can go ahead and plug in. So we have here, I'm going to move the 120 over, so this would be negative 30 equals, what is that, 80 e to the negative 45k. Notice then where this stuff comes from. We're going to go ahead and we would subtract, move everything over, and then simplify. Alright, and don't forget the negative here on the 80 that I did just a second ago. Also, it looks like there's a slight typo. Notice here there's the 30 and the 80. When we divide both sides by negative 80, the negatives will cancel. Those zeros will cancel and we'll get 3 over 8. And this here should have been a 3 instead of a 7. However, I also just double checked. The decimal here is correct with the 3, so don't worry about that if you're trying to follow along. Now, once we know what the k is, and notice here the k is roughly speaking, or rounded to 4 decimal places, 0.0218, that then gives us our k. Remember, the k here is fixed to the blood plasma. So even if we put the blood plasma in that second oven, this k is still going to stay the same. Okay? So now let's see. So we've solved for a, we solved for k, which means we actually have the full formula here, but the key thing we were trying to find is that k. So, next thing that we would do is we'd set up our second oven. Remember, this here was a 3, not a 7. It's going to go away to be 3 even each time. Go away to be 7 each time. So in the second oven, we know we've got a temperature, a room temperature, a surrounding temperature in the oven of 140. So here, what we've got is we've still got the A is the same, the K is the same, this decimal right up here. The 140 switches out, so now with this new function, we're good to go in terms of answering the question. Okay? Notice, because we were actually dealing with the same blood plasma, we were going to get a lot of the same answers. The only change was here what the temperature was of the surrounding medium. So the next thing is we want to solve for time when temperature is 90 degrees Fahrenheit with this new equation. So what we would be doing here is we would be setting this new equation equal to 90, and then we would be solving for t. And I'm going to assume that you guys can do that, okay, on your own. Okay. When you do that, that solution, that t that you would find after doing a little bit of algebra would be in decimal form 21.56355.275 minutes, which of course you would, depending on how accurate you need it to be, round it and either say it's between 21 and 22 minutes. It looks roughly about 21 and a half minutes. Or if you need to be really precise, you might go down to the seconds. All right, so let us look at a second Newton's law of cooling question. And in this one here, we're going to, instead of doing everything really quick, we'll go ahead and go through the full process. So for this guy, we've got a cup of coffee. This cup of coffee is initially at 95 degrees Celsius, so it was just made, and it's going to cool to 80 degrees Celsius in 5 minutes while somebody set it on the counter in a room temperature of 21 degrees Celsius. And I on purpose picked two different questions, one Fahrenheit, one Celsius. Okay. So we're going to use Newton's law of cooling, and we want to determine when the temperature of the coffee will reach 50 degrees. So this is literally, we want to know T, not Celsius time. We want to know that T, that time, when we're going to reach the 50 degrees. So let's pull out all of this stuff first. So that's the first thing. And when we pull out all of the information, we know that we're going to use Newton's law of cooling. So we go ahead and grab that formula. We know that the room temperature is the 21 degrees Celsius. We know that our initial temperature of the coffee, so of the stuff we care about, is 90 degrees. We know that in 5 minutes, the coffee is cooled to 80 degrees Celsius. So we've got now here, not just that T of 5 equals 80, but I went ahead and mentioned here that we've got our time is in minutes. I probably should have mentioned, but didn't earlier, that temperature is in Celsius. Okay. So the next thing we'll do is we're going to set up our differential equations. We are a differential equations class, so I do expect you to be able to set up the differential equations for these type of things and actually solve the differential equation. So here, when we set up our differential equation, notice the only thing that we're plugging in is that m. And we're going to have to solve for k here. One of the things that I would definitely recommend is I would recommend always factoring out the negative here. It'll make your life easier, but that's personal preference. All right, so key pieces of information just copied from the page before. We've got our differential equation, and in this case, it's totally separable because we've got these two factored pieces. So separable differential equation, move everything to each side. So separate out your t's, make sure all the capital T's are on one side, all the lowercase t's are on the other side. And notice this looks identical to when we did it before when there was only letters involved. Here the only difference is there's no m, we've got the 21. Okay. So the same format, we'll go ahead and take the antiderivative of both sides. When we take the antiderivative of the fraction, we'll get a natural log. And when we take the antiderivative of this negative k, remember k is an arbitrary constant. It's fixed to coffee, but we don't know what it is yet. We'll have negative kt. Don't forget your constant of integration. Biggest issue people have, forgetting the constant of integration. Now, this is a perfectly fine answer if all you cared about was what's the solution of the differential equation, but we actually want to answer a question. We want to know what's the lowercase t, what's the time when capital T over here equals 50. So we need to actually solve out for our temperature. In order to break temperature out of a natural log, take both sides and raise them to the e. And when we take both sides and raise it to the e, the natural log cancels on the one side, and the other side, you're going to have the negative kt in the exponent of e, and the plus constant here will just be some coefficient. So we'll go ahead and move that all over to one side. So we'll get that the actual function is temperature is 21 plus a, which we don't know yet, times e raised to the kt. K we also don't know yet. But we have two pieces of information, initial temperature and then temperature 5 minutes later. So we'll be able to solve for a and k. Really, really nice one is initial temperature. So here we'll plug in t equals 0. So the e component will totally disappear. We'll plug in 95 for our temperature. So we have 95 equals 21 plus a, which solve for a, and you'll get 74. So what we know so far is 21 plus 74 times e to the negative kt. We still don't know what k is, but we do have our second condition. So we plug in for our second condition. So for our second condition, we'll get 80 equals 21 plus 74 times e raised to the negative 5k. And this is where we do a little bit of algebra. We'll move things to the side and then take the natural log of both sides. Okay. So in order to do that, first we'll subtract 21 from both sides. If we subtract 21 from 80, that should be 59. We'll have 74 times e to the negative 5k. Yes, that's trying to be a 74. So then we'll have 59 over 74 equals e to the negative 5k. Then we'll take the natural log of both sides. So we'll have natural log of 59 over 74 equals negative 5k. And then to solve for k, we'll divide by negative 5 on both sides. Once you have what k equals, that was the only thing missing in our function back here, and we would have what our actual function equals. So fly that in. So k equals that mess that we just said. So when we plug it in, we'll have the actual answer for our function is 21 plus 74 times e raised to the, and I just inserted what k was into the expression. So negatives will cancel and we'll get t times 1/5, so t over 5, times that natural log. And if you want to put it in a decimal, that's okay. You're going to be more accurate if you keep it in the natural log format, but it's also a little bit more unwieldy. Well, it's fine if you're keeping track of things, but more to remember, I should say. Okay. Or if you want to be fancy and do the trick that we looked at before when you have an e and a natural log in the exponent, you can also simplify it to this. That's totally personal preference. All right, so now last thing is you answer the question. Because remember, in a story problem, it's not just getting to the answer of the differential equation, you're now using it often. So we wanted to find the time when temperature equaled 50 degrees Celsius. So we'll go ahead and we'll grab our equation that we just grabbed, and I went ahead and typed in the fancy format. You don't have to do this. So we'll have 50 equals 21 plus 74 times the mess. We'll then solve. So we subtract 21 from both sides. We'll divide by 74 on both sides. So that's this. And then we get that 29 over 74 equals 59 over 74 raised to the 5, t over 5. Take the natural log of both sides, and at this point you're going to start looking the same if you left it in e's or not. If you left the function in terms of e's or not. So the natural log of 29 over 74 equals, now this t over 5 was in the exponent, so it pulls out front, so t over 5, natural log of 59 over 74. Notice this looked like our k times t, except it's negative. That's totally fine. This looked like our exponent, negative k times t. Now, if we still want to solve for t, we've got to get rid of both the natural log and the 5, so we'll divide by the natural log and multiply by 5, which will give you that t equals 5 over natural log of 29 over 74, all divided by natural log of 59 over 74, which looks like a mess, but you plug it into your calculator, and you'll get that this is 20.7 in a whole bunch of decimal places. So this tells you that at just under 21 minutes, your coffee is going to cool down to the 50 degrees Celsius that the person who was grabbing this coffee wanted it to be. Okay? And that's the crash course in Newton's method.